Okay, I think it's recording. So I share screen. Yeah, I hit record. Okay, yeah, it's recording right now. I don't know where that's going. Hopefully somewhere on my desktop that I can find. I'll figure that out later. All right, so um, we have temperature, and we're plotting it as a function of heat. That's essentially what a heat curve is. And you're starting out with something that's in, typically when you're looking at these, you start out as a solid, and then you progress through to a liquid, and then ultimately to a gas, which I'm going to represent with these little specks here. Okay. So yeah, so what I was saying before with no visual aid is that as you go through these, the experimental setup that you're trying to imagine in your mind is that all I'm doing is I have I take something, like let's say I'm trying to do this experiment at home. I'm trying to generate one of these heat curves. You would just take a ice cube and maybe put it in some sort of vessel. You want to keep things at constant pressure because that's usually what we're working at. I've got my temperature probe in here, and I'm just applying heat down here. And then I'm just monitoring what happens. As this goes through its phase transition and melts to a liquid and eventually goes to a gas, I'm marking off on the temperature probe what happened. So I'd end up generating a plot. And then I'd fit that plot. And what I would get out of it, I'm going to get rid of the points on it. What I would get out of it once I fit the data is something that looks like this. And so I was saying the intuitive part of this is like as you apply heat to something, you expect the temperature to go up, right? That's like just basic everyday experience. If I put my hand in a fire, it's going to get hot, and that's what happens, and that's what we see for part of the curve here, right? But then as we get towards the phase transition, we end up seeing is that things flatten out, and that part's not nearly as intuitive. So if you were applying heat at the phase transition of something, and you're measuring its temperature, you might, I mean, initially, if I wasn't familiar with these systems, I might think like my thermometer is broken or something, but that's not what's going on. There's something just different happening at the phase transition. And then once you get past the phase transition, things pick back up. And then you see it plateau again at the phase transition. So there's something weird that happens at the phase transition. But before the phase transition, it should be fairly this part should make sense, that as I put in heat, the temperature is going to increase. And from a quantitative perspective of just trying to solve these problems, the two equations that we end up working with are Q is equal to M times, C sub P times delta T. That's the first equation. And the other equation is just something that relates to, we'll do that one in a second. That one relates to the enthalpy of the actual phase transition. But let's take a look at this equation really quick. So when we look at this equation, so one thing you got to get good at that I feel like we don't do a good job of teaching in high school or really at any level is, like, I think the tendency when you're looking at chemical equations is just kind of turn your brain off. And I'm guilty of this too. You start plugging in numbers, and it's hard to really draw the connection between like what the equation actually means and like what all this other stuff over here is that we're talking about means. They almost feel like totally separate, and you just kind of plug in numbers, and at the end you get a number and you're like, man, I hope that number is right, and you have like no real intuition about whether it's right or not. And there's no way to like really completely connect the two. At least I don't know, maybe people who are really good at math can. But it's good to kind of have some intuition around like what you're looking at. And so when we look at this equation, you can kind of break it down into making some sense, which is to say that like all it's really saying is that as I heat something up, I'm going to use a different color. So as I heat something up, that's what Q is. The temperature changes. That part makes sense. That's like if you had to start out and somebody was like, write an equation for how heat is related to temperature, you would say, well, as I add heat to a system, the temperature is going to increase. And And then, so what do these other things here mean? This is just the mass. So this is heat. And it's equal to the mass of whatever you're heating times, we'll get to what this is, times the change in temperature. If you were to write this out in plain English, it would look something like this. So all of those parts of this equation should look reasonable. If I'm putting heat into a system, I expect the temperature of that system to change. And the more stuff that I have, like the more stuff that I'm heating, I'm going to expect the temperature change to be dependent on that. So, if I think I say this in my other lecture video, but if I'm boiling water or something, if I'm boiling a tablespoon of water, if I take the same amount of heat, let's say, and I apply it to a tablespoon of water, I'm expecting the temperature of that tablespoon of water to go up much more dramatically than if I apply it to a whole swimming pool or something of water. And that's all those pieces of that equation are really telling us. The part of this equation that's new or different is this C sub P part. And so C sub P is the heat capacity. And heat capacity is a little bit harder to wrap your head around. I mean, honestly, all of these things, I don't know. We could run a Solomon problem. It's only 9:30. Heat capacity is the really hard thing to wrap your head around, or at least for me, just because it's not something that you really have a good intuition for. And honestly, just differentiating between heat and temperature can be kind of a challenge because they feel, and I talk about this in one of the lecture videos, they feel similar because the way we talk about them colloquially. But heat capacity it's a property of a substance that it's just how fast the temperature of a substance changes as I apply heat to it. And so, yeah, the heat, in this particular case, we're talking about the specific heat capacity, which has a definition that sort of like ties it to a specific substance that's independent of the mass. And that's really what I'm trying to get at here. But like if you take like a chunk of aluminum, for example, and measure and put let's say your experiment for trying to understand what heat capacity is, it would be like if let's just say I took a glass of water. Glass of water. Is that a good one? Yeah, let's do a glass of water. I was trying to think of something. I was going to say a glass of water and a glass of acetone, but that's like a weird example. You guys might have some experience with acetone. That's what's in most fingernail polish removers. All right, so I've got a glass of water here, but I also have a glass of oil. So I've got a glass of like olive oil or something. I don't know. It's not. Maybe it's a little bit spoiled to be this color, but whatever. You get the idea. But so I've got oil, and I've got water. If I take a certain amount of heat, like you can even just imagine a hot plate. So I take 2 hot plates, let's say, and I turn them to the same level. So I'm applying heat from a hot plate, and I put them on whatever level, like 5 or something, whatever. It doesn't really matter. But just imagine that you're setting them up and you're kind of controlling for those 2 variables. So I start heating them. They're the same volume or the same mass of oil and water that I have there. And on the top of this, I have a temperature probe. So just a thermometer. And I'm just measuring how the temperature changes as the heat kind of flows into it. So the experiment here is literally like I just have 2 hot plates that are identical, and I set them to the same setting, like 3 or 4 or something on there. It doesn't even matter as long as they're the same. And then I'm just measuring the temperature as time changes. What I would see is the temperature of the oil is going to change a lot faster. The temperature of the oil is going to change a lot faster than the water. And you might have some intuition around this. Like if you ever put something in a hot pan on the stove, like if you put a little bit of oil in there into a hot pan, the oil gets hot really, really fast. Whereas water, on the other hand, takes a lot longer to come to temperature. And the reason for that, because they're the same mass, I'm adding the same amount of heat and stuff to them. And the reason for that is that they have different heat capacities. So this one the temperature is going to change a lot faster, that means that it has a much lower heat capacity. So heat capacity in a sense is like how resistant a substance is to temperature change. How resistant is a substance is to temperature change as I put heat into it. So the faster the temperature changes I put heat into it, the lower the heat capacity. So things that are good insulators generally will have really high heat capacity. They can hold a lot of heat without actually having their temperature change. Water is something that actually has a very high heat capacity. And you know this if you have lived out in like California or something. Things are generally like cooler near the ocean. And that's because the water actually is pulling heat away from the air. It can kind of hold a lot of heat. Um, yeah, so that's heat capacity. So that's what the C sub P measures or is a measure of. It's a measure of how resistant, this is like I don't know what the exact definition you would give for heat capacity is, but it's a good way to think about it. It's just how resistant something is to temperature change as I heat it up. Yeah, is it the same? Is it kind of the same thing as specific heat? Yeah, it is. Usually when we talk about specific heat, we're talking about the specific heat capacity. So they're not just this kind of the same thing, they're identical. So there's different ways to talk about this number, that's heat capacity, which is what I'm saying, which is like how temperature varies as you put heat into a system. There's specific heat capacity. There's specific heat capacity at constant pressure, which is what we're generally looking at in chemistry. They have it at constant volume. You can use ones that are not specific. That's where it's very dependent on the mass of the substance that you have there. But ultimately, it's the number that you're looking at is just an expression of how resistant things are to uh, um, how resistant. Got it. Now I'm trying to say it again. It's how resistant the substance is to temperature changes as I add heat into it. Yeah. And so when you're not using the specific heat capacity, so the specific heat capacity sort of normalizes everything, so you don't have to worry about the mass. Uh, when you're not looking at the specific one, then the mass matters. So you would talk about like, so for example, going back to that thing where you have a tablespoon of water versus a pool. Well, a pool of water is going to have a significantly larger heat capacity than a tablespoon of water, just because you have a lot more of it there. So it's going to take a lot more heat to move the temperature of a pool 1 degree Celsius as compared to a tablespoon of water. Okay, so specific, so that's what heat capacity is. Specific heat capacity kind of normalizes for mass. So you would just say, well, the specific heat capacity of a tablespoon of water is the same as the specific heat capacity of a pool of water. It's just it's more of a property of the substance, even though they're measuring the same thing. So anyway, so heat capacity is the least intuitive of the bunch. And honestly, even just getting the difference between heat and temperature can be a little bit tricky sometimes, just because of the way we think about those. And I go into that in more detail in one of the YouTube lectures. All right, so coming back up here, so what all we're doing right now is just kind of building a like a picture of what this looks like, this whole process. In terms of problem solving, uh, the first part here is we always use whenever the slope is not flat, basically. If the slope is not horizontal, so the slope is anything other than 0, we end up using this equation Q is equal to m times C sub P times delta T. That's what's going on in all of these. I'm not going to rewrite it over and over again. But anywhere that the curve is blue, we end up using Q is equal to m times C sub P times delta T, excuse me. Yeah, what changes then? And I didn't do a really good job of showing it here. What's going to change between these is that C sub P, the heat capacity for ice, is going to be different from the heat capacity for liquid water, which is going to be different from the heat capacity of the gas. So the heat capacity is a property of the substance, but it also is a property of the phase. So ice versus liquid versus gas, they're all going to change temperature differently as you heat them up. And I forget exactly how it changes. I should probably know that, but I forget exactly how it changes if the heat capacity increases or decreases. We could probably parse it out if we thought about it, but it's not super important for what we're learning about. But ultimately, when you look at this, right, Q equals M times C sub P times delta P, this is a linear relationship. This is a linear relationship here. And we see that when we look at the graph up here, that we're getting lines out of this, right? We're calling it a heat curve, but there's really no curvature here. And so the slope, C sub P, this is the slope of the line on that heating curve or whatever. So C sub P is literally this change here, or it'll be reflected in this change right here. And so the higher the heat capacity, the lower the slope. Like the slope is going to change. And this kind of gets back to what we're talking about down here when we look at the oil and water type thing. So this one, the temperature of the oil is going to change a lot faster because it has a much lower heat capacity. So if we're expecting, sorry, I keep bouncing back and forth, but if we're expecting the temperature to change rapidly as I add heat, then I'm going to expect the slope of the line to change faster. Right? So something with a high heat capacity is going to be really like gentle change, because as I add heat to the system, the temperature is just going to change very slowly. So I'm not going to be moving up on the horizontal temperature axis very fast. And if it has a really low heat capacity, then it's going to change really rapidly, right? So maybe something dramatic looking like that. So that's how to think about heat capacity, I think. But ultimately, when you're kind of given these questions, if it's now we can work a problem. Yeah, I really need like a giant screen. Let's see. Yeah, so let's just start out and kind of ease our way into these heat curves, because ultimately it starts to feel a little bit overwhelming, especially when you're going through the phase changes, but you end up doing the same thing over and over again. I don't know that we necessarily need a heat curve, but I'll draw one anyway. All right, so let's just say I have an ice cube. And it's at minus 50 degrees Celsius. So that's pretty cold. That's colder than a standard freezer by a good bit. And then I'm just going to change the temperature from minus 50 degrees to minus 10 degrees Celsius. Okay, so the phase transition and we're at, unless I say otherwise, we're always at 1 atmosphere of pressure. So chemists, because we're usually working, if you've ever been in a chemistry lab, we're working at atmospheric pressure. Like you're working in a fume hood, you're not working in like a vacuum chamber or something like that. So generally we're at constant pressure. So that's almost always what we're talking about. If you go on and take physics or something, you'll get into these other scenarios a little bit more deeply. But yeah, so we're at 1 atmosphere, and all we're doing is we're applying some heat to the system, and we're measuring the temperature, and it's going from minus 50 to minus 10. So the question that we could ask then is, how much heat is required let's say to heat an ice cube from minus 50 degrees Celsius to minus 10 degrees Celsius. Okay, so as I phrase this question, it's a pretty reasonable question. I've got a chunk of ice and I'm just raising it from 50 to 10. What information did I not give you, or is this enough information? I'll just tell you it's not enough information. What information is missing from this problem in order to solve it?
Mass.
Okay, so I'm heating this up. Mass. Okay, good. You guys are quick. Yeah. All right. Yeah. So the two things are, well, the first thing is mass, right? So like you can think about this, you don't even have to think about the equation. It's just like if I have a giant chunk of ice like an iceberg versus like a tiny ice cube, right? That's going to affect how much energy I have to put in to melt it. Okay, so even not even thinking about the equation, it just should be intuitive that like, yeah, the mass is going to matter for how much heat I have to put into the system. How much heat I have to put into the system. Um, so yeah, so we need the mass. So what's the mass going to be? I'm just making this up. So like, let's say we have, let's say we have 45 grams of ice. Yeah, 45 grams of ice. So we're talking about H2O here. Okay, and then the heat capacity or the specific heat capacity, C sub P. Um, this is something that's usually, I mean, especially you guys are taking this online. Is the specific heat of water the same heat capacity of ice? Good question. Um, so I had this problem even while I was lecturing. So water, when we talk about it in normal life, right? Like a glass of water, you just assume it's liquid. We talk about water, but like here, we have to be specific. Are we talking about liquid water? Are we talking about solid water? Are we talking about gaseous water? But I know what you mean. So somebody asked, is the specific heat of water the same as the capacity of ice? The answer is no. The specific heat capacity changes depending on the phase. And we could talk about why that's true microscopically. Uh, I'm gonna look up the heat capacity of ice right now. This is giving it to me in, what is a specific? I'm looking at some random internet source. So one thing about internet sources is like they're not always right. Oh, good. Thank you, somebody who looked it up. ICE 2.04. I was about to put the wrong damn thing, so I'm glad somebody said that. All right, what are the units on that? 2.04 grams per degree Celsius, joules per, okay, joules per gram degree Celsius. Thank you. Or 2.09. All right, so again, a very important thing to do, hopefully you got out of your system or into your system, whatever you want to think about it, in general chemistry. The first one is you absolutely need to keep units, especially when you're dealing with stuff in thermodynamics. So we'll jump around, not we as in, like, as in like the subject jumps around between like joules, kilojoules, kilograms, and then sometimes because chemists are weird, they'll use calories or kilocalories. And so if you get your units wrong, especially in a multiple choice test, then you'll lose all your credit, which is not what we want. So be really careful. Be a really good bookkeeper is just good advice, especially for you guys who are trying to be engineers. Try to keep track of your units really carefully. That is the more complicated your calculations get, the more useful they are. All right, so now we have the heat capacity of ice. So liquid water, somebody posted in the chat, and solid ice have different heat capacities. And I guess what I'm looking at is the heat capacity of water. Liquid water is higher than that of ice. So we could reflect that in a plot. But yeah, so I'm going to be specific here. I'm going to say this is of ice. All right, so now we can come and look at our equation and we can say, okay, we've got all the stuff we need here. So we know that delta T that's given in the problem is going from minus 50 to minus 10. So we're looking at a change of 40 degrees Celsius. And then C sub P, I've already written, so I'm not going to rewrite that. Yeah, so now it gets into that familiar territory where it's like, I'll rewrite it all out. Now it gets into that familiar territory where it's like, I am just plugging in numbers. And I don't know that I have a pretty, like, with some problems, I feel like I can kind of know what I'm expecting in terms of the output of it. This one, I'm not completely sure. But the main thing to make sure of here is like, one thing to always check, especially in the thermo chapter, is that all your units make sense. So I'm looking at joules. I guess that doesn't really matter that much. But my mass unit down here and my mass unit there are the same. Because sometimes it's in moles, sometimes it's in grams. It could also be in kilograms. And if it's not in if they're not all the same, you want to be able to convert. And the thing you want to convert is always going to be the mass. Okay, so don't mess around with the constants that we give you or that you look up. Don't mess around with the heat capacity if you're trying to do a conversion. And then also you'll notice that delta T is in degrees Celsius, and this is in degrees Celsius. So what I do, like when I'm trying to figure out what the proper units to get are, is I look at whatever the constant is. Here it's, kind of the heat capacity is the thing that you're typically given as like the constant you look up. Or I would look at R, which is, the ideal, like if I'm doing a gas law thing, I'll look at the ideal gas. What is that thing called? The constant R equals, 8.314, and look at all the different units on that. So somebody asked, when we're assessing delta T, do we need to keep signs negative or positive for change? You should come out with a positive number for the change. I think the change should always be positive because it's the final minus the initial. Is that right? Minus 10, yeah. Right, am I thinking about that right? So if temperature initial is H cubed, so if T sub I, so delta T is, delta always means the final minus the initial. So T sub F here is going to be minus 10, and then that's minus a minus 50. I'm already breaking my own rule with the units, but you see that the minus signs go away, so it ends up being minus degrees Celsius, 10 degrees Celsius plus 50 degrees Celsius, so you end up getting 40. So changes should always be positive. Can it be negative if you're lowering the temperature? Is that true? I don't know. If you come up with one that's negative, I guess what I'll say is I don't know just off the top of my head what every single scenario is, but my instinct is that delta T should always be positive. Regardless, let's see. And maybe, I guess you're right, because Q could be negative. Regardless, as long as you follow this, you're solid, right? So take T sub F, whatever your final temperature is, and subtract your initial temperature and plug that in. And whatever the sign changes on that is the appropriate sign change. You don't arbitrarily just assign a sign to the temperature, I guess I'll say, right? It's guided by this equation of taking the final minus the initial. And I might be wrong that it's always positive. Maybe I'm wrong about that, but that doesn't really matter. Yeah, there are probably ways, because like let's say you started at 0 degrees Celsius and you increase the temperature. So your final temperature was 10 degrees Celsius. So you're going from 0 to 10. No, let's say your final temperature, I see. Yeah, if your final temperature was negative 10, then it'd be, yeah, okay. So you can have a negative one. You guys are right. But yeah, just stick to this equation and you'll be good. Don't just arbitrarily assign a sign there. There are arbitrary signs that we use, just isn't a place where we use them at. Anyway, so yeah, so now it's like familiar territory. We just go in and we plug all these in. Q is equal to 45 grams, and then we want to multiply that times the mass. I'm sorry, that is the mass. We want to multiply that times the specific heat capacity. And then we multiply that times delta T, excuse me. And then that gives us some number. But if it's the other way around, the negative 50 adding 10 would be negative. Same here. Did I mess up? All right, there seems to be a little bit of questions about this temperature thing. Let's check this out real quick. I'm certainly not immune to making mistakes. All right. Let's just get rid of that. What's our final temperature here? It's minus 10 degrees Celsius, because I'm going from minus 50 to minus 10. T sub F equals minus 10 degrees Celsius. What's the temperature that's initial? That's going to be minus 50. So I'm just subtracting those two. So T sub F minus T sub I is equal to minus 10 minus 50. I lost my units on there. But so this ends up being a plus because, minus, minus, and minus, whatever. And then we end up getting 40 degrees Celsius. Yes, so it should be positive 47. Since you said that it has to be positive, I gave, oh, I say, okay, yeah. Yeah, no, you're right. Yeah, I agreed with you eventually. I just, I misspoke. Thank you Yeah, doesn't always have to be positive. Yeah. Okay. So anyway, so yeah, so we get some number out of this. Yeah, which you guys already have. We get joules. So, when I go in here, this problem's pretty straightforward, but I always go in and make sure that all my units cancel. So if you screwed up somewhere with your joules is the unit of heat just because that's the units that we looked up for heat capacity. Significant figures, I don't know, man. I mean, I guess if you really want to, we could worry about significant figures here. On the exams, we give you multiple choice. I try not to be super particular about the significant figures so that if people are off by a little bit, it's fine. Significant figures matter. Oh, yeah, I guess. Oh, God, you guys have another class. That's right. Okay. All right. So this is a very small part of these heat curves, but it's if you can work through this part, you can work through the entire heat curve. We'll put together in our next problem solving session, we'll put together the rest of the heat curve, and I'll show you how the ones that feel really complicated and long are actually just like it's just doing the same thing that we just did over and over again. But anyway, you guys have a good day. My office hours are today at 2, I think, 2 to 4, and I'll see you guys there. But thanks a lot, and yeah, I look forward to working with you guys on Monday on the rest of this stuff. Bye, y'all.